Hello students, for the BSc 5th sem and in the paper 6 I am dealing with Raman Spectroscopy, and here you know Raman, a well-known scientist of India. He awarded Nobel Prize in 1930 for his work on the scattering of light and for the discovery of the effect named after him, and he discovered in the Raman spectroscopy 1928. So before going to the Raman spectroscopy, you must know about some of the concept: scatter, absorption, adsorption, and diffraction. So here scatter. So here you can observe when a ray of light incident on a molecule, the energy here, the energy scatters in all the direction. Okay, this is the incident radiation, this is the incident radiation. So these all are the scattered radiation in all the direction. Okay, this is scattering. And then absorption, when a ray of light incident, it absorbs the energy, it absorbs the energy. It is a surface, this is a surface, and it absorbs the molecule or surface, absorbs the energy. And adsorption, that means for a adsorption, other molecule which stick on to the solid substance, it's just a stick on to the solid substance. So this is the adsorption, this is enough. And diffraction is no need for this concept. First, the spectroscopic technique used to observe the vibrational, rotational, and other low frequency mode in the system. In a system, the spectroscopy technique we can use for vibrational, rotational, and low frequency modes. For this, we are using spectroscopy. And Raman spectra is similar to infrared spectra. It deals with scattering of light and not with its absorption. So here, very important, it only deals, that it means Raman spectra only deals with the scattering of light, not with the absorption. Only deals with scattering. That means incident radiation is not important here. The scattered radiation is important. Okay, here we can't calculate absorbed radiation or absorbed energy. Only the incident energy we can calculate. So there's a difference. In the Raman spectra, we are only dealing with scatter radiation, and in infrared there's normally, and other spectroscopy, they are using the absorption light. That means how much light absorbed, that we can calculate. So here it deals with the scattering of light and not with its absorption. Raman effect is the phenomena, this is the definition. Raman effect is the phenomena in which the frequency of scattered light from a sample is different from the frequency of incident radiation. That means the phenomena in which the frequency of scattered light from a sample, scattered light frequency from a sample is different from incident light. So here the scattered light have the different frequency compared to incident light. So this phenomena is called Raman effect. And here the theory of Raman spectroscopy. When a beam of monochromatic light, so this is the direction of light here. When a beam of monochromatic light or radiation passes through a transparent medium, so this is the medium, transparent medium here, of energy h nu. The energy of incident radiation is h nu, you know that. And the molecules of the medium and a part of light is scattered. That means molecule of the medium. These are the molecule of a medium here. When a light is falling on a molecule, it scatters radiation. Okay, it scatters the radiation, and this scattered radiation, for example, when it incident on this molecule, just imagine, then it scattered the radiation. Then we are measuring the scattered radiation 90 degree in the angle. So here we are measuring the light in 90 degree, that is scattered light measured in the right angle, and then we will get the graph or a signal graph here. And this is the total basic principle here. And then there are another type of scattering. It is called relic scattering. What is relic scattering? It is the elastic collision. Elastic collision means what? So you can see the animation here. The elastic means when a ray of light, just imagine, when a ray of light incident on this molecule, this excite to higher energy. This, just imagine, this is the higher energy, this is the higher energy, and it comes back to the ground state. That means it comes back to the ground state by releasing how much amount of energy, by releasing how much amount of energy is absorbed. Same energy it will release. So it is called elastic. So the collision is elastic, then the scattered photon will same frequency and same energy as that of incident light. So incident light and scattered light have equal energy. There is no difference. It is called Rayleigh scattering. And here, when a photon collides with the molecule gets excited. So it will get excited when this is the animation, the physical animation, not the radiation animation. Okay, to understand the concept. So when a light fall here, so it excites to higher energies. Just imagine this is the higher energy, and it comes back to ground state like this. Molecule excite to higher energy state from ground state. When the molecule returns to the same ground state, so it returns to the same position here. It returns to same position here. Okay, not to the other position. Same, the scattered photon have the same frequency. This one time I repeated. So the scattered photon have the same frequency as that of incident photon, is called telescattering. And then this second concept here, Raman scattering. Here there is a difference. If the collision is inelastic means the incident radiation and the scattered radiation, they have different in their frequency. For example, here you can understand. So this blue color is line is incident radiation. Just imagine, when incident radiation have this much of energy, this blue color energy, and when in the case of Rayleigh scattering, it will come back to the same energy state from excited state to the lower energy state. You see, this is the excited state, and it comes back to the same energy level. So this is the same energy level. But in the case of Raman spectroscopy, it excites to the higher energy. It is common. So when the ray of light is incident on this electron, it excites to the higher energy. But what happens? It come back to not the same ground state. So it not come back to the same ground state. It come back to a virtual higher energy state. This is the virtual higher energy state of higher energy state. Okay, this is the ground state. You know, here it excited from here to here. So it come back for the next higher energy state. Or it may happen like this: the electrons from the higher energy state Okay, just higher energy state to another higher energy state, and while coming back, it goes to the ground state, complete ground state. That means lower energy of excited energy level. So this is the ground state while exciting. This is the ground state while exciting. In this case, this is the ground state. And after the releasing of energy, what happens? So after releasing of energy, it comes back to the lower energy state. So lower energy than this one, lower energy than this one. So there's a difference, there is a gap between these two energy level. So these two are Raman scattering. So Rayleigh scattering means when the electron excites to higher energy, it will come back to the same lower energy state. Okay, and then in the Raman spectroscopy, it excited from excited from lower energy to higher energy is common, but while coming back, it not comes to the ground state. For not for this ground state, it will come back to just higher energy of that ground state. So here it will stuck here. Okay, so there is an energy gap between these two energy levels. This one, or it may happens like this, from just higher energy state to an extra higher energy state when absorbing the energy. So here to here it excites, and while coming back to the ground state, it not coming to this position, it coming to the lower energy state. So there is a gap. So these two are the Raman scattering. So here the incident photon, so what happens? There is an energy gap. So there is an energy gap between incident radiation and the scattered radiation. So here energy gap between incident radiation and the scattered radiation. Raman scattering. When the incident photon collides with the molecule get excited to a higher energy state from the ground state. When the same thing here, when the incident photon collides with the molecule get excited to higher energy state from the ground state. If the molecule returns to higher energy state and not to ground state, the energy of scattered photon will be less than the incident photon. So just go through the second point here. If the molecule returning, while returning from higher energy to lower energy, while returning the higher energy state and not to the ground state, so this is the ground state, so from higher energy to not ground state, so this is the ground state, not to the ground state, the energy of scattered, so while coming back it scatters some amount of energy. This energy, okay, this energy, scattered energy, is less than, it is less than that. Why it is less? So here to it jumps here, not to here. Okay, same thing I explained, that's enough I think. So there is an energy gap. This is the incident radiation. Here the excited electron, when a ray of light incident on this electron and it excites, but while coming back it not coming to the excited ground state. Okay, it just stick on to the next energy level, next higher energy level. So there is an energy gap between these two. Okay, and so the incident radiation have higher energy compared to scattered radiation. Is next point. A series of equal spaced lines are obtained at a lower frequency, and then the Rayleigh scattering. These are called Stokes line. So this what the molecule returns to the higher energy state to state and not to the ground state, the energy of scatter photon will be less than the incident radiation. So energy less than the incident radiation, it's called Stokes line. Okay, it's called Stokes line. And here we have to observe one thing, there is a equally spaced lines. That means, so here this is the equally spaced lines, this is the spaced equally spaced lines. So here this is the Rayleigh scattering, it is in between these Stokes line and anti-Stokes line. So here I will explain anti-Stokes line First I explained Stokes line and I will explain anti-Stokes line now. Then I will explain the energy gap. What is that energy gap and comparing with the Rayleigh line here. When the incident, this is for anti-Stokes line. Okay, this I explained for Stokes line. When the incident photon collides with the molecule get excited from higher energy. As I said, in now the electron, excited electron, come back. While coming back, it just stick on to the higher energy level of ground state. So this is the ground state. So it's here. Just imagine the electron is here. Now what happens when a ray of light incident on this electron will excite to higher energy state. Okay, this electron excite to higher energy state, and while coming back, it come back to the ground state, no ground excited state. So this is the while coming back, the molecule get excited from higher energy state. So here the molecule get excited from this state, and while coming back, it it prefer or it prefer for this lower energy state. Okay, and in the molecule directly returns to the ground state, the scattered photon will have higher energy than the frequency of incident. So what happens? So it exited from here, and while coming back, it directly returns to the ground state. So the incident radiation have this much of energy, and while coming back, adding to this much of energy, it added an extra energy. So incident radiation have lower energy compared to the scattered radiation. So it is called anti-Stokes line, and here their position in the frequency graph here, you just see here, you can understand easily here. This is the Rayleigh scattering. So excited from here to virtual state and coming back to the same ground state. There is no loss in the energy or gain in the energy. So equal energy is scattered and equal energy is incident here. And next, H nu, this is for Stokes line. H nu is incident, and only this much of energy is scattered. Only this much of energy is scattered, and this much of energy is not scattered. So it prefer for this ground state. Okay, it's prefer for this ground state, and this is Stokes line. And then anti-Stokes line means the H nu is incident energy, and while coming back, the electron prefer for the ground state here. Okay, this is the still excited state here. This is the still excited state, and while coming back, this is the energy H nu, and this is the energy H nu, and this is the added energy from this Stokes line. So this have H nu plus, that means anti-Stokes line have H nu, the incident energy radiation, and H nu m, that is the added energy. This is the added energy. So it have higher energy than incident radiation. And here is the intensity. So normally the intensity of Rayleigh scattering is common. Rayleigh scattering is very common, so it has high intensity. That means most of the electrons prefer for this Rayleigh scattering. So here intensity of Rayleigh scattering is very high. Then second prefer stage is Stokes line. Okay, second one is Stokes line. It's so in some of the molecule, not all the electron in the molecule, not the electron. Some of the electron they prefer for Stokes line, but very rarely it prefer for anti-Stokes line. So most of them are prefer the electron excitement prefer for this Rayleigh scattering, and next to the Stokes line, and then at last only few in numbers they prefer for anti-Stokes and scattering. So their intensity like this. You see, this is the intensity. is the intensity. So its intensity is very low in the case of anti-Stokes line, and in the case of relics, that is laser, that means first what energy is incident, same amount of energy is scattered. So there's a relics, so it have high intensity. And in the case of Stokes line, most, not all the electron, some of the electron compared to anti-Stokes line, it have higher frequency. So it have higher frequency, and it have very low frequency, only this much of intensity it have. Here not frequency, it is the uh, intensity. Okay, it have only small intensity and it have very high intensity here. Okay. So then distance, just see here. And one more thing, wavelength, as I said, wavelength is inversely proportional to, is very important, you know, I think wavelength is inversely proportional to its energy and the frequency. So wavelength is inversely proportional. What it means? That means smaller the wavelength, higher the energy and higher the frequency. Frequency is higher or energy is higher means it have smaller frequency. Okay. So here, just see here, anti-Stokes line is in lower wavelength, that means it have higher energy, so it have high energy compared to anti-Stokes line. The wavelength of Stokes lines are higher, so 575, this is 500. So when we go for wavelength, lower the wavelength means higher the energy, or higher the wavelength means lower energy. It is inversely proportional. And then this all that I explained. That means h mu means frequency. So this is a frequency, and intensity also explained. Then intensity is explained once in the previous slide here, explained. But relics lines are highly intense. Stokes lines are less intense than relics line, but more intense than anti-Stokes line. Anti-Stokes lines are least intense. And then Raman shift is very important. The Raman shift is a difference in the frequency or wave number. Raman shift means difference in the frequency or wave number between the incident and scattered light. So this is the Raman shift. Here, difference, delta stands for difference, and this is frequency of incident radiation, and this is the frequency of scattered radiation. So this is Raman shift means what? The Raman shift is the difference in frequency or wave number between the incident and scattered light. In terms of wave number, we can say this is the wave number. Wave number means what? Mu dash is the wave number. So here mu dash, that means it is the wave number of incident radiation. It is the wave number of scattered radiation. And we have one problem. And in the live classes, that means offline classes, I will go through the problems, but just try to understand the problem now.